So till now we have discussed the no load current and the inrush current in a practical transformer, right? So now we will get the equivalent circuit. All of the assumptions that we have made for an ideal transformer, that we are going to address one by one, so that how a practical transformer will look like, okay, and we will get its equivalent circuit. First we are going to model the no load current. So the no load current, it had two components. What were the two components? The magnetizing component and the core loss component. Now the magnetizing current, this is going to be lagging the induced EMF by 90 degrees, right? And the core loss component, this is going to be in phase with the induced EMF. So how you are going to model this? The magnetizing current, you can take it as the current through an inductor, right? So if this is the inductor and the voltage across this is the induced EMF, then if current IM is flowing through this, now the current through an inductor, it will lag the applied voltage, the voltage across it by 90 degrees, right? So that's why we are modeling with the inductor. And next IC is in phase. So this we will take as a resistor, okay? Now this is IC, you add both of them, you're going to get I naught. You can call these as the shunt parameters. Shunt parameters of the equivalent circuit. Next what we have, the winding resistance, okay. So this is going to be nothing but this can be modeled as a resistor, and through this resistor what will be the current that is passing? See, if you consider the transformer core like this, and this is the winding. Now here V1 voltage is applied. Now this winding has some resistance. Now through the resistance, what is the current flowing? This current, if you take as I1, then current I1 is flowing here. This is important point here, okay. And next we have the leakage flux, right? This was another assumption. Now the leakage flux, this is going to be modeled in terms of an inductor, and through this also the current flowing is I1, okay. Now using these 3 points you can get the equivalent circuit. First we will draw the windings, both the windings on the magnetic core, okay. So this is the core and this is the primary. Here you have the voltage source, applied voltage source, and here you have the secondary, okay. So this you can take as N1 turns, this you can take as N2 number of turns. So now you can draw the equivalent circuit. First we will have the resistance of the winding, and then we have the inductance which is accounting for the leakage flux, okay. And this is going to be the shunt parameters. Here you have the inductance and this is the resistance, okay. Now this is the primary side. The secondary side, you are going to have the winding resistance and the leakage flux, but there will not be any shunt parameter, okay. So here first we will mark the voltages and the parameters. So this is the primary side voltage. You can, in some textbooks they use V1, or you can also write as VP. P means primary side, but we will use both of them interchangeably. Now this resistance we will take it as R1, and this inductance we will take the reactance which is X1, and the current we will take as I1, okay. And what is the current that is here? This is the no load current I0, and this will be the magnetizing current IM, and this will be the core loss current, okay. Now this inductance we will name as XM, the magnetizing reactance, and this resistance is the core loss resistance RC. Now what about this current? This is going to be I1 minus I0. We take it as I2 dash. So why we are taking it as I2 dash, you will understand later. Now what is this here? This is nothing but the ideal transformer representation. So that means this voltage will be, if you take it as E1 and this voltage, if you take this as E2, these are the actual induced EMFs, okay, and the voltage and current ratios that we have discussed for ideal transformer, they will be applicable to this voltage, okay, they will not be applicable to this voltage. So you can write E1 by E2 is equal to N1 by N2, okay, and this here we have the secondary winding resistance and the leakage flux, okay. So this we will represent as R2 and this as X2, and what is the current here? This is going to be I2. Now we can write the current ratios as well. Here the current ratio will be applicable between I2 dash and I2, not I1 and I2, okay, please remember that. So this here you can write as I2 by I2 dash. And also one more thing here is, in order to distinguish this ideal transformer from normal inductors, we will represent a coupling sign here, okay. This means that there is a coupling between this winding and this winding. So this is the exact equivalent circuit. We are going to get some approximate equivalent circuits as well. Now one problem with this circuit, with this equivalent circuit, is the analysis is not exactly easy. We have a primary and a secondary side. The voltage levels on both the sides, they are going to be different, okay. Now what can we do to eliminate this part and make it into a single normal network circuit, right? So this is achieved by means of impedance transformation. So first we will see what is the impedance transformation. So we will consider this ideal transformer, okay. So here the current that will be flowing on the primary side, this is going to be I2 dash, and the current on the secondary, this is I2, okay, and this is the ideal transformer, remember. Now if you have an impedance here, a load impedance whose value is ZL, okay. Now this voltage, let this be E2, and this voltage, let this be E1. Now what we want to eliminate this part and we want a simple impedance, okay. Then what we will need the equivalent impedance as seen from this side. So this, if you take as ZL dash, what will be this ZL dash? This is going to be E1 by I2 dash. So now we will try to express ZL dash in terms of ZL, and if this is the number of turns, if this is N1 and this is N2, then we don't want in terms of voltages and currents, but in terms of this impedance value and the turns, okay. So what will happen here? ZL, we know this is E2 by I2. Now E2 you can write in terms of E1 as how much? N2 by N1 into E1, right? Next I2 you can write in terms of I2 dash as N1 by N2 into I2 dash. So this is going to be how much? N2 by N1 whole square into E1 by I2 dash. But what is E1 by I2 dash? It is ZL dash. So finally you are going to get ZL in terms of ZL dash as ZL dash into N2 by N1 whole square, okay. So ZL dash is going to be ZL into N1 by N2 whole square. So what will happen to this circuit? This circuit you can draw as, you have an impedance here whose value is ZL dash, this voltage is E1 and this current is I2 dash, okay. So in general any impedance, they can be referred to either side, okay. So that means, let us say this is the transformer primary and on the secondary we have an impedance Z2, because it is secondary I am taking it as 2, subscript 2, and now you want to refer to the primary side, then what will happen? You will get an impedance here which is Z2 dash. So Z2 dash is equal to N1 by N2 whole square into Z2, right? These are the number of turns. This is N1 and this is N2. Now here this voltage, this is going to remain the same, and the same current that is flowing through here, this is going to flow through here. Similarly, if you have a impedance on the primary side, this is Z1, let us say, okay, and here you have the primary winding, this is the secondary winding, okay. Now this you can refer to secondary side, okay. Referring to the secondary side means this voltage here, this is if it is E2 and this is I2, this is going to remain as it is while we don't bother about what is the current and voltage on this side. So what you are going to get here, this is going to be Z1 dash and this is going to be E2 and this is going to be I2. What is Z1 dash here? This is going to be N2 by N1 whole square into Z1. So here you can see the difference. This is N1 by N2. So when you are referring from secondary to primary, what is coming in the numerator? The primary turns. When you are referring from primary to secondary side, then what is coming in the numerator? The secondary number of turns is coming in the numerator, okay. So this is the impedance transformation. Using this we can get a equivalent circuit which does not have the ideal transformer part anymore. Now with this information we will try to get the equivalent circuit referred to the primary side, okay. This was the exact equivalent circuit, right. Now this what we are going to do, R2 and X2 we are going to transform into the primary side. We are basically referring to the primary side. So what will happen, R1 and X1 they will remain as it is, and the shunt parameters also they will remain as it is, there will be no change. Now this R2 will become R2 dash here, which is equal to what, N1 by N2 whole square into R2, and similarly this will become X2 dash. This is going to be N1 by N2 whole square into the original reactance, okay. And here you are going to have the ideal transformer, right. This is how we got the impedances towards the primary side. Now what will happen to the voltages and currents? This voltage, primary side voltages and currents, they are going to remain as it is. Here this no load current is also going to remain as it is. This is magnetizing core loss current. What about this current? This is going to be I2 dash. What about E1 and E2? This is going to be E1 and E2 is now going to be referred to the primary side. So it will become E2 dash. What is that? This is equal to N1 by N2 into E2, okay. So this is how the voltage will be transformed when it is being referred to the other side, okay. So you can see here that E2 dash, it is nothing but E1, whether you see by this formula or you see by the circuit. In either way you can see that E1 is equal to E2 dash. And what about this voltage here? This is going to be also V2 dash. What will it be? This is going to be N1 by N2 into V2, okay. But remember, V2 dash is not equal to V1, only E2 dash is equal to E1. Now this ideal transformer part we can simply ignore for our analysis. What is the circuit finally? The equivalent circuit referred to the primary side, it is going to be R1, X1, shunt parameters XM, RC, and here you have R2 dash and X2 dash, and the currents are going to be I2 dash and this is I1, and the voltages are going to be V1 and V2 dash. This is V1 and this is V2 dash, okay. These currents also they will remain same. This is the equivalent circuit referred to primary side. Now similarly you can get for the secondary side as well. So what will you get here? Now all of the primary terms, they are going to change. This is going to become R1 dash, this is X1 dash, and this is going to become V1 dash. Similarly, the shunt parameters Xm dash, Rc dash, and the secondary side parameters, they are going to remain as it is, R2 and X2. Okay, what is this current here? I1 dash, and this current is I2. Here this voltage is going to be V2. Okay, what about this current? This is also going to become I0 dash. This is the equivalent circuit referred to secondary side. Now here one particular point that I want you to observe here is, in the exact equivalent circuit, here the very initial circuit, we took this as I2 dash. Okay, now we got the equivalent circuit here with reference to the primary side like this. Okay, now here you can see I2 dash is nothing. Whenever there is a dash, it means that it is being referred to the other side. So here we have I2 dash. For this reason, to get this sort of uniformity, we have taken I2 dash in the beginning itself. Okay, now we will discuss approximate equivalent circuits. Okay, that means we are making minor changes so that the equivalent circuit, it becomes much simpler for analysis, right? So in the exact equivalent circuit, when it is referred to the primary or the secondary side, what happened? There was an extra node here, right? And here we have the magnetizing branch. Here we have the secondary winding resistance and leakage flux. Now here you can see there is an extra node. This is the input node, this is the extra node, and this is the output node. In order to avoid this, what we do is, this magnetizing branch, we bring it to this side. That means what? If the current, this is I0 and this is I2 dash, let us say we are referring to the primary side, then what will be this current? In terms of I0 and I2 dash, it will be I0 plus I2 dash. Okay, but now since the no load current, this is I0 is the no load current, right? Since it is very small, the drop due to this current along this parameters, it is going to be very small. That means if you take this impedance as ZP, okay, primary side impedance, then the voltage drop across this is going to be I0 plus I2 dash into ZP. Since I0 is very small, you can almost approximate as I2 dash into ZP, right? That means the current that can be flowing through this is I2 dash, even then there won't be much difference. Okay, so this is how we will get the first approximate equivalent circuit. Okay, so first we will draw the circuit referring to the primary side. Okay, then what is going to happen? You're going to have the magnetizing and the core loss components first, right? And here you are going to have the primary and the secondary series parameters. This is R1, this is X1, R2 dash, X2 dash, and this is going to be RC, XM. What about the voltages? This is going to be V1, this current is going to be I1, but this current is going to be I2 dash, and this is V2 dash. Okay, further we can just simply write this as, draw this as, here you have an equivalent resistance and an equivalent reactance, and this is the shunt parameters, core loss component and the magnetizing component. This current is I1, now this is R equivalent 1 you can write, and this is X equivalent 1. Okay, here the voltage will be V1, this current will be I2 dash, and this voltage will be V2 dash. What is R equivalent here? R equivalent 1 is R1 plus R2 dash, and X equivalent 1 is X1 plus X2 dash. Similarly, if you are referring to the secondary side, referred to secondary side, then you're going to get like this. The structure, it will seem as it is, only the parameter values it will change. This is going to be R equivalent 2, okay, that is being referred to the secondary side, and this is X equivalent 2. And what about this? This is RC dash and this is XM dash, okay. So what is R equivalent to here? This is R1 dash plus R2. X equivalent to is X1 dash plus X2, okay. And what is RC dash here? This you can write in terms of the RC and the turns ratio like this, okay. Says XM dash is equal to XM into N2 by N1 whole square. Similarly, you can write for R1 dash. R1 dash is going to be R1 into N2 by N1 whole square, okay. Similarly, X1 dash. So this is one approximation. You can further approximate. You can entirely ignore this shunt parameter branch, okay, because the current that is flowing through this is going to be very small, right? Here we have not written the voltages. This is V1 dash, this is going to be I1 dash, and this is going to be I2 and V2, okay, because this is referred to the secondary side. The secondary side parameters will remain as it is, while the primary side parameters are going to change, okay. So now in comparison to these currents, the current through this parameter, this branch, it is going to be very less. So we can ignore this entire branch as it is, okay. Then what you are going to get the approximation? The final approximation, this is what we will often use. This is going to simply consist of one resistance and one inductance, okay. So if you are referring to the primary side, then we will call it as R equivalent 1, X equivalent 1, okay. And here what you have? I1 and this is V1. Here what you have? I2 dash and V2 dash, okay. This is referred to the primary side. Okay, so here also you can write final approximation is ignoring the shunt branch altogether. Because load current is very small, okay. So when you are referring to the primary side, R equivalent 1, this is going to be R1 plus R2 dash, X equivalent 1 is going to be X1 plus X2 dash. Similarly, you can draw the circuit referred to the secondary side. Then what you are going to get? The structure is going to be once again similar, only the values will change. This is R equivalent to, this is X equivalent to, okay. And this is going to be V1 dash, this is I1 dash, and this is I2, this is V2, okay. And what is R equivalent to here? This is going to be R1 dash plus R2, and X equivalent to is going to be X1 dash plus X2. So this is the final approximation, final equivalent circuit that we will use more often, okay.